Something subtle happened today with 3I Atlas. It wasn't the kind of flashy event that makes the evening news or trends globally, but for the dedicated teams who have been tracking this interstellar comet for weeks, it was significant. These are the experts who know every pixel and every data point, and what they saw was, and enough to make them quietly return to their workstations and update their predictive models. There wasn't a massive outburst or a spectacular new tail stretching across the horizon. Instead, there was a shift, the kind of nuanced change that hints at whether this object is finally stabilizing or simply catching its breath before an unpredictable new phase. If you've been following the journey of this comet, you know its behavior has been anything but normal. It has consistently refused to fit into the neat categories we've established from centuries of studying comets born within our own solar system. Today's update doesn't provide all the answers, but it adds a vital piece to a puzzle that has been equally frustrating and fascinating for astronomers worldwide. The update began much like any other day, with teams gathering fresh imagery, brightness readings, and positional data from a network of telescopes and spacecraft positioned throughout the solar system. They compare this new information against yesterday's best estimates of what the comet should be doing. On most days, you expect routine adjustments. As a comet moves further from the sun, it typically dims. Its cloud of gas and dust quiets down, and the orbital path requires only minor tweaks. That is the standard procedure that followed the rules. However, today's data told a different story. The first anomaly the teams noticed was the comet's brightness. When they plotted the latest measurements against the standard models for how a comet should fade, 3I Atlas was still performing brighter than expected. It wasn't wildly off course like it had been during previous outbursts, but it certainly wasn't following the smooth decline predicted by the textbooks. It's as if the comet is stubbornly clinging to its glow, refusing to dim at the rate dictated by physics. While this stubbornness has been a recurring theme, what truly matters is the way that brightness fluctuates over time, because that reveals the internal mechanics of the object. To understand this, scientists analyzed the light curve, which essentially tracks how the comet's brightness changes as it tumbles through space. Every comet spins, and as it does, different parts of its surface are exposed to the sun and visible to Earth, and if there are active jets of gas and dust shooting out from specific spots, those regions will brighten and dim rhythmically as the comet rotates. Just a few days ago, that light curve was a mess, a chaotic heartbeat with multiple peaks of varying heights and inconsistent timing. And it was a picture of beautiful, fascinating chaos, with jets firing seemingly at random. Modeling that kind of activity is nearly impossible, much like trying to predict the path of a leaf in a windstorm. You can describe what happened, but you can't predict the next rotation because too many independent forces are at play. Today, however, the curve looks remarkably different. The main peak remains the dominant feature. That's the large active region that has been consistently venting material since we first started observing, but the smaller ragged bumps that used to spike and drop randomly between rotations have smoothed out. Instead of 3 or 4 erratic humps, there are now 2 consistent secondary rises that appear at the exact same point in every single rotation cycle. The comet has transitioned from chaotic noise to something complex but rhythmic. It is the difference between hearing static and a song that has a clear, recognizable structure. And this is the first subtle shift. The activity hasn't ceased, but the way it presents itself as the nucleus spins has become much more organized. The vents that used to flicker on and off without warning seem to have settled into a predictable pattern. Perhaps the surface has reorganized itself, or certain active regions have finally won the competition for which cracks get to vent. Whatever the reason, the heartbeat of the comet has found a rhythm. The team then turned their attention, but in today's data, while that stretch bar is still visible, it has become noticeably rounder. The brightest region is no longer hugging one side as aggressively as before. The light has redistributed itself, making the inner coma more symmetric than it has been in a long time. That sharp, off-balance look has softened. It's like watching a lopsided wheel gradually wobble less as it spins. Even the tail spine, the bright central line of the tail, looks cleaner and less turbulent where it connects to the nucleus. These are subtle, detailed changes that require careful side-by-side comparison, but they are consistent across multiple observations. Then there's the matter of the orbit, which is where the trajectory specialists find their most compelling evidence. Every comet is subject to gravitational forces from the Sun and planets, which can be calculated with extreme precision. However, active comets also experience non-gravitational forces. When jets fire, they act like miniature rocket engines, pushing the nucleus in whatever direction they are pointed. If these jets fire asymmetrically, they can speed up or slow down the comet's rotation, or nudge its orbit in ways that gravity alone cannot explain. Tracking these forces is essential for predicting where the comet will be in the future. For several recent updates, astronomers have struggled to match their models to reality, often having to make major adjustments to account for the erratic behavior of 3I Atlas. It was like trying to predict the path of a leaking balloon. Today, for the first time in quite a while, those adjustments were minimal. The extra acceleration from outgassing is still present, and the object isn't just a dead rock, but the direction of that. The push didn't wander. When the software refitted the data, it suggested a smoother, more stable trend over the past few days. This is a significant result for orbit analysts because it suggests that the underlying activity driving these forces has become more predictable. The comet is still pushing itself around, but it's doing so with newfound consistency. When you line up all these observations, the smooth light curve, the rounding of the inner coma, and the stabilizing orbital thrust, you get a picture of an object whose internal chaos is organizing. These are the kinds of subtle shifts that make scientists lean forward in their chairs. So, what could be causing this? One possibility is that we are witnessing the comet emerge from its most chaotic phase. Immediately after its closest approach to the Sun, 3I Atlas behaved like a nucleus under extreme stress, with layers of ice vaporizing, deep pockets of volatile material venting, and thermal stress causing the surface to crack and shift. This created a feedback loop where new vents would change the spin, which would then change how the Sun heated the surface, leading to even more cracks. In that kind of environment, everything looks wild and unpredictable. But today's data suggests that these competing processes might be starting to align instead of random on and off behavior. And across the surface, a few dominant regions seem to have taken over and are now venting consistently. This would naturally smooth the light curve, create a more balanced distribution of gas in the coma, and provide a steadier, more predictable thrust for the orbit. This is the optimistic interpretation. 3I Atlas is finding a new equilibrium and adapting to its current environment as it moves away from the Sun. However, there's also a more cautious interpretation to consider. We have seen comets do unexpected things before, and sometimes a period of apparent calm is actually a warning sign. So it's possible that the remaining activity has simply focused into a small. While this makes the comet look more organized from the outside, it could be concentrating immense stress on those specific regions. Think of it like a crack in a dam that suddenly becomes the main leak. From the outside, the flow might look steady and predictable, but that single crack is now taking all the pressure that used to be spread across many points. This focused flow can erode the structure faster and lead to sudden, catastrophic failure. And we've seen comets fracture or explode before when internal pressures became too much. We might be watching 3I Atlas settle into its long-term outbound configuration. We could then track it for months or years, learning invaluable lessons about its composition and history. If, on the other hand, this is just a brief pause before another chaotic shift, today's calm is simply a breath between surprises. So regardless of the outcome, these small updates are incredibly important. With interstellar objects, We learn just as much from the subtle changes as we do from the big dramatic events. Each data point tells us how these visitors hold themselves together under stress and how they adapt when conditions change faster than they can handle. We've only ever tracked a handful of these travelers. Oumuamua was the first, and it left us with more questions than answers. Borisov was the second, and while it looked more like a traditional comet, it still had its own unique quirks. Now, 3I Atlas is the third, and it is teaching us once again that so we cannot make assumptions based on our local experience. Each of these objects offers a window into the diversity of the galaxy. Every day brings new measurements and new opportunities to understand the universe in a way we never have before. Stay curious, because this story is far from over.